divided by 2. All right, so my x is equal to, these 2's will cancel, negative b over a divided by 2. All that work for a little tiny equation. The equation for the axis of symmetry is x equals negative b over 2a. All right, the nice thing about this little formula is it's quick and easy to find that axis of symmetry. However, you don't get the vertex directly from it. You're going to have to do a little more work to find that vertex. So let's take a look at an example, and let's work through one and see what you might do to find this. All right, so here's your example. We've got g of x equals 2x squared minus 5x plus 2. First question, will this be concave up or down? And does it have a max or a min point? Remember, we get that from our leading coefficient, which is 2. 2 is positive. That indicates that we are concave up. Okay? And if we're concave up, we have a minimum point down there at the bottom. All right, next we're going to find the axis of symmetry, but this time instead of completing the square, we're just going to use our formula. X is negative b over 2a. All right, so our b value is negative 5, so the opposite of negative 5, of course, is 5 over 2 times 2. So my axis of symmetry is x equals 5 fourths, excuse me. All right, now to find the vertex, we got our x value, but we're going to have to find y. And the way you do that is to plug back into your function. So even though completing the square might have seemed like a lot of work, you're still doing quite a bit here. So either method is about the same amount, especially when you have a fraction. All right, so plug your 5 fourths in. We get 2 times 25 sixteenths minus 25 fourths plus 2. So finding that common denominator, we've got 50 sixteenths minus 100 sixteenths plus 32 sixteenths. All right, so our g of 5 fourths is going to be equal to negative, what will that give us? All right, we got negative 50 plus 32, so negative 18 sixteenths. All right, and that's going to give us, if we reduce, that'll break it down into negative 9/8. Or, for graphing purposes, it might be easier to think of as negative 1 and 1/8. All right, that takes care of finding the vertex. To graph this, you would want to continue by determining your x and y intercepts, and then by sketching a graph using those particular points. And I'm sure that you've gone through that before, so I'm not going to take the time. But as a class, you may want to stop the video here, find your x and y intercepts, and then sketch your vertex, your axis of symmetry, those intercepts, and then get a rough generalization of what that graph would look like had it been graphed. All right, what we're going to finish up with today, though, is we're going to take a look at doing some quadratic modeling. All right, and doing some quadratic regression. When you have real data, when you've got real data, oftentimes, again, it's not perfect, and we have to be able to find a model to fit, just like we did with the linear equations. So the first thing we're going to do is start by collecting some data. All right, and to collect the data, we're going to cut the cheese. All right. All right, you are going to take a slice of cheese, and everyone in the room is going to cut the cheese. All right, so we're going to take our knife, which yours is going to be a ruler and a pencil, and we're going to make a slice through our cheese. And then what you're going to do is you're going to count the sections that you made. Well, here I made, obviously, one slice created 2 sections of cheese. So in my table here, I'm going to record 2. All right. Take your knife, pencil and ruler, and cut again. All right, now I've created 4 slices. So here I'm going to place 4. All right, one more time, and then I'm going to give you an opportunity to finish it on your own. When you go to cut, you're trying to get the maximum number of slices you can from any one cut. So as I cut through here, you can see that I would get 7 different slices. 1, 2, 3, 4, 5, 6, 7. But if you're not careful, if you cut through a point that's already an intersection point, you're only going to get 6. So your job, your goal, is to try to get the most slices you possibly can out of your cheese. All right, if you'd like to do this on your own, you can go ahead and stop the video at this point and continue collecting data. All right, if you didn't want to finish it, or if you've already finished collecting your data, let's take a look at what we get. All right. Here, I'll get it off the screen again. By cutting several different times, up to 6 slices, I gather the following data. Now, I've got red dots on my slices to help me count them, but with 6 slices, you should have been able to get up to 22 different pieces. All right, so let's come back and let's talk about what we're going to do with those now that you have your data. Okay, just like we did with the linear functions, we're first going to check, number 1, to see if it's linear. And if you remember from the last lesson, we do that by finding our first differences. So very quickly, if I find the first differences for my y values, 4 minus 2 is 2, 3, 4, 5, 6. Okay. Clearly not linear. Those values are increasing every single time. They're not constant. So this wouldn't be modeled by a line. A line would not be a good choice. For quadratic functions, you check again, you check a second difference to see whether or not it's going to be quadratic. So let's subtract again. We're going to subtract our differences this time. So 3 minus 2 is 1, 3 is 1, 5 minus 4 is 1. 6 minus 5 is 1. If my second differences are constant, if they all end up being the same number, I know it's a quadratic function that will model this data well. All right, so let's get out our calculators and take a look at how to do that one more time. All right, go ahead and enter that data into your calculator. Make sure your plot is turned on. All right, and then go ahead and set your window or use Zoom 9 to set it for you. I'm going to cheat and use Zoom 9. Be lazy here, Zoom 9. And I can see that this graph, it doesn't look too bad. Maybe a line would have fitted okay. But if you can look at that graph, you can clearly see that there is a curve right here. You can see that there is concavity. Now, one thing you need to know about real data is, remember what the graph of a quadratic looks like. It looks like a parabola. Oftentimes, though, in real data, you're only going to get to see half of it. All right, you're only going to see the right side of the curve usually, because a lot of times in real life, values below 0 don't make any sense. For example, in our cheese slicing, can you cut a -1 slice? Okay, it doesn't make sense. So don't be looking for a parabola necessarily. Be looking for at least half of a parabola. All right, to find the model that fits it, it's the same procedure we use for linear. Stat, and then you slide to calculate, and then just look down your list till you find quadratic regression. And you'll see on number 5, you've got quadratic regression. So we're going to choose 5. as long as your values are in L1 and L2, from here, if you punch your button, you'll see the equation. But if you remember, you can let the calculator store it for you by hitting vars, yvars, function, y1, and then enter. And there's our equation. So our equation for this quadratic would be y equals 1/2 x squared plus 1/2 x plus 1. Now, if you'll hit graph, we can take a look and see that this model fits really, really well. Okay, and in fact, because my second differences were all 1, this guy is perfectly quadratic. In other words, there's no variance whatsoever. All right, however, you know that in real life, things aren't really going to turn out that nicely. So let's take a look at one more example of some real data. Okay, let's see if we can zoom in a little bit here. All right, if you take a look at this data, this is the population of Cleveland, Ohio from the 1900s to 1980. All right, and you can see, get it all in there, we go. You can see that after I checked my first differences down here, they're crazy. I've got 178,000 here, I've got -7,000 here, definitely not linear. However, even when I check my second differences, which I've already done here, you can see they're still not the same. I have 57,000 here, -132,000 here, 28,000 here. Not a lot to go on. So I'm still, just looking at my first and second differences, I'm still not sure what model would most appropriately fit it. When you've exhausted your 2 tests, you need to check visually. So we need to go ahead and graph this data. So if you will, again, enter the data into your calculators. And for me, I went ahead and entered it into L3 and L4. Remember from talking about linear functions, usually we don't enter the entire date. We assign the first day to be our initial value 0. So my x values are years since 1900, okay? Years since 1900. So that would be 0. 1910 is 10.